2. All right. So after that period of discussion, and now returning, I set the learning objectives of a design philosophy, these barriers and drains, that it comprises system components, and how might design practice develop with time. And if we look at the components, and I use this to guide it, then one aspect of the development of practice with time is with regard to how might we assign interface friction. And that's something that I think is a work in progress. There are schools of thought, publications such as you saw for discussion exercise number 3, and peak or residual, and is residual stress dependent, and might we choose a composite interface? That I would say that's a body of work that's in progress, and to some extent it mirrors 1 or 2 progressive insights into residual strength of clay e-soils themselves. That might fall under emerging practice and components and the interface strength between components. Let me turn to the hydraulic conductivity, and I'm going to focus on this leachate and collections system, again by selectively looking at a particular body of work. And it's this process of what's influencing the way we think that I'd really like to impress upon you. Okay, so now with regard to this page in the notes, I'm going to say, let's look at the system components, and let's consider Rose. 2005 was the publication, Rankin lecture. It was actually the 45th Rankin lecture. Okay, and let's look again at evolution of design practice and the philosophy and how we want system components to work. And so for that, it's quite a monster lecture. I have to say, look at this. 631 to 678, so 45 plus pages of Geotechnical paper. It's an astounding commitment by Kerry Rowe to write it up. And here's our philosophy. These are the latest findings. Those are the latest findings of 2005. In fact, remind me to make a comment as to subsequent work of Kerry Rowe. So, what's the deal? We're going to be looking at leachate collection systems, and Kerry makes some recommendations on leachate collection systems. That's what I'm going to focus on in here, but I'm going to put it in context of some of the other ones, the latest findings with regard to leachate collection systems, but we'll place that in the context of other the other objectives of his lecture. But philosophically, again, just stepping back up to the philosophy, I think it's a very elegant observation in his introduction. Most modern landfills at the time of writing, 2005, have been in operation for less than 20 years. Okay, and so it's not a huge body of work to be able to draw upon, but the question arises as to what are the key factors that influence the long-term performance, all right? And this paper addresses it. In fact, he looks at 7 key factors. Okay, so let's go in and acknowledge that he looks at 7 key factors. I'm going to draw this down here. I'm going to put times 7, and let's say, please turn over. We'll get to it in a second. Okay, but 7 key factors, and his interest is long-term performance. And if we consider the leachate collection system, that's that uppermost drain. All right. And along the way, we have a little schematic figure number 1, which is really capturing the essence of the BC system and the US EPA system, and so on and so forth. We'll skip through this page because on page 634, he gives a very nice game plan to the lecture. Okay, this lecture is going to focus on 7 key issues relevant to the long-term performance. Okay, and what are those 7 key issues? What are they? He begins with, let's move up to here, he begins with clogging of the leachate collection system. There's that leachate collection system. And this is going to be the one of the 7 that I'd like to speak to in detail, and to examine the development of design philosophy and how it has evolved with time. The others that he works towards, if we capture them, he speaks to issues of temperature. Where's that? Yeah. Speaks to issues of temperature of the liners, of design philosophy and system. And this is going to be the, what are they? He begins with, let's move up to here, he begins with clogging of the leachate collection system. There's that leachate collection system. And this is going to be the one of the 7 that I'd like to speak to in detail, and to examine the development of design philosophy and how it has evolved with time. The others that he works towards, if we capture them, he speaks to issues of temperature. Where's that? Yeah. Speaks to issues of temperature of the liners. He also speaks to leakage, both advective and diffusive. Okay, so there's making that advective and leakage that's diffusive. He goes on to examine factors that control the service life. He examines the potential for desiccation of clay liners, and then wraps it up with long-term performance and field experience. In fact, combinations of field and lab experience almost permeate throughout it. So does that make 7? 1, 2, 3, 4, 5, 6, 7. Yeah, there we go. And let's draw out of this the leachate collection systems. Okay, so over the page, the long-term performance of the leachate collection systems. And he goes on to construct an argument, I think elegantly so, that it's actually very important. This drain is very important to maintaining the integrity of the liner and therefore the long-term performance of the system. The leachate collection system is maintaining the integrity of the primary barrier. So what is leachate? We get a little statement, okay. and it's going to have physical, chemical, biological properties. It would be hazardous if those properties, or special waste, hazardous waste, if those properties exceed certain thresholds. The leachate collection system represents a critical component of the system, and its primary function is to control the depth, or the leachate head, on the underlying liner. And he speaks to the evolution. The design has evolved considerably over time. Okay, the earliest form was a toe drain and/or perimeter drain. So you know, it's almost the culture of slopes coming in here, right? The next generation of leachate drainage systems was French drains in conjunction with pipes. Okay, and everything is to try and control the standing level. It's an under drain to the waste, and you're controlling the standing level, not so much because of poor pressures and effective stresses and slope stability drainage, but because of the aggressiveness of the fluid for the service life of the barrier. Okay, and then we move to modern leachate collection systems, or continuous blanket. The under drain is now essentially a gravel blanket, and a regular pattern of pipes. Okay, so in the world of philosophies and developments of design practice, here is the configuration of the arrangement changing. And that might lead us, for example, if we look at a blanket, then in the Keel Valley landfill, where Kerry Rowe has done a lot of work over the years, as it comes to the more regular, or more recent rather, the leachate collection system consists of a granular drainage blanket. There's how thick it is, 50 millimeter washed crushed gravel. Okay, and if we take that into consideration with our BC scenario, originally we had a hydraulic conductivity greater than 1 × 10⁻³ that in the BC regulations. US EPA is saying greater than 1 × 10⁻², and Kerry Rowe is observing that the development of design practice has taken us to remarkably permeable drains because of the manner in which they may be compromised over their service life. And as evidence in support of claims that he makes, it's almost a body of evidence. He speaks to field examples of clogging. Okay, so clogging has been observed in landfills, right, that have had a wide range, right. So just because you got a big drain doesn't necessarily prevent it. So we've had clogging from French drains, continuous sand and gravel layers, and in systems both with and without geotextiles. That would be a geotextile between the drain and the waste, the overlying waste, and he cites a whole bunch of case studies going through this table too, and speaks to the collection system and observations from it. Okay, so we've had an evolution in the geometry and an evolution in the materials from which it's built, and the field evidence in support of claims shows that when this clogging occurs, we have both biochemical and a growth of biofilm and also precipitation. And what this is doing is reducing the porosity and thus the conductivity of the material. So we want to try and have something that its primary job as a leachate collection system is to be permeable and remain permeable. And the argument is that's an important function for the durability of the barrier below it. Otherwise, it's sitting in a pond of this leachate. But the action of the biofilm growth and the precipitates is to compromise the porosity and thus cause the hydraulic conductivity to lower. Okay, and if we follow this through, then turning to page 639. The field data for the Kiel Valley landfill, the field data, suggests that the clog material is being formed by biological processes, right, and the precipitation. This is almost a summary statement, and so this drove them to do complementary work in the lab. Findings from laboratory cells, flow cells, and column tests, and the lab work is really confirming what's happening in the field. So can you see it at the lab scale, and can you see it in the field scale? And in moving to the labs, they started to run tests with flow cells. So these lab mesocosms, it's a flow cell, and they set these up to examine, well, what if we considered variations, right? So they're trying to simulate in the lab. It's a bit tricky because of the temperature issues at full scale and real time, and they set up various, let's call it a parametric study. Okay, so they're getting the waste material, and they've got variations where there's a filter or a separator between the waste material and the gravel, and different separator layers were examined, right? And they speak to their experiment, the lab experiment, with a woven geotextile separator, a non-woven geotextile separator. There's a filtration opening size or apparent opening size, and experience with graded granular filters. Okay, and then chase down into the details of them. And out of that came some conclusions with, again, we're still in the leachate collection system, but clogging of geotextiles. Okay. The field and the lab flow cell studies that although geotextiles can clog, when used appropriately, they can minimize the clogging of the underlying leachate collection system. And this is an important feature. I think it's an elegant one, and I've chatted over the years with Kerry about this. Development of design practice and design philosophy. And this gets captured in both of these points, okay? So the geotextiles can clog, but if they clog, in all likelihood, you're going to minimize clogging of the underlying leachate collection system. And how does that work? If we jump ahead to the page 644, which I hope should be the next page in your notes, it gets captured here. Typical, it's an under drain to the waste, basically. And either there's a geotextile on top of the drainage gravel, or there may be a sacrificial or a sand protection layer and a geotextile, and then the drainage. And the argument is that, you know, there will indeed be a potential to clog And if the clogging is occurring because of precipitation and or biofilm growth on surfaces, do you want that clogging to occur on the leachate? Sorry, do you want that clogging to occur? Let's put clogging here. Would you prefer that any clogging tends to happen on a, oops, let's just get that back, on a upper surface to your drain? Does that mean that you may even have local, I'm going to use the word perched leachate? I'm going to try and capture that. Let's do that here, and let's do that here. Let's label this as, it's not a perched water table, but it's a perched leachate. And let's call it mound, for want of a better word. It's a perched leachate mound. But if that's happening and it's not mounding on top of the barrier system itself, then everything that gets associated, the undesirable consequences of the leachate mounding directly on top of the barrier, which can include elevating temperatures and greater hydraulic gradients across the barrier and greater gradients of concentration of chemical constituents. So your advective flow and your diffusive flow is greater with the mounding directly on the barrier. But if the mounding is elevated above it, then that can produce desirable or relatively desirable outcomes. Okay. Without chasing through all of the details, that's the emerging philosophy. And the understanding is that these will mound and then perhaps break through and drain off, and mound and break through and drain off. But that this process is more attractive than having the drainage gravel itself become clogged. So I guess that's the main comment that I wanted to make. And sometimes I get asked questions about, well, what about, do you recommend a woven or a non-woven? I almost was involved, but it doesn't look like it's going to go ahead for a little advisory role on a project on the Sunshine Coast. But I wanted to try and catch needle punched non-woven geotextiles provide a particularly large area for biofilm development. But everything clogs in a similar way. Geotextile clogging follows a similar pattern to that for granular materials. Right? And buried in your notes, this is a point I wanted to make. Buried in your notes, let me take you back to this page, which was from the notes on material properties 2. And if you remember when we were looking at the transmissivity of geonets and the fact that the transmissivity of the geonets and the flow rate of water through the geonets was a non-Darcian flow regime, I happened to show there complete clogging with biomass if it was done with leachate, not water. And there were the data for a gradient of 2%, which is about the basal surface gradient of a waste containment facility, 300 kPa, which is less than the crushing strength of the geonet. The water continues to flow through, but the leachate essentially clogged it entirely with a biofilm within 100 hours. This kind of clogging can occur, and clogging of geotextiles follows a similar pattern for granular materials, and indeed follows a similar pattern for geonets. So, in terms of what we might do about that, remove this here, and we get a little bit of text to complement the philosophy. Then based on the available evidence, as summarized earlier, and it is in the paper, it appears desirable to design the leachate collection system. Now here's the evolution of design practice: to maximize leachate treatment while maintaining its design. Under these circumstances, using a design such as that in figure 6, and K. Rowe uses his words nicely, may be desirable, provided the perching of leachate on the filter doesn't have any negative side effects. And that's a beautifully written caveat by someone who has provided some very, very good advice over the years to owners, including those of the Kiel Valley. Now, if I go back, and I'm going back to go forwards, but if I just remind ourselves of the context, I said I wanted to target the latest findings with regard to leachate collection systems. And that's what we've done, and that's how we end up where we are here. And we observed that that was one of seven key issues, was clogging of the leachate collection system, and then there were another 6. So as we leave the leachate collection system within the ranking lecture, and we go to the conclusions. The conclusions will go hunting for the leachate collection system, but then we expect that there's going to be a number of companion, in fact 6 additional comments. Okay. Now, K. Rowe is an absolutely fantastic communicator, and if we take those conclusions, I think he is very wise to observe that many of the studies may cause us over time to revise the present findings. I think that's an absolutely fantastic context in which to put the conclusions that follow. Thus, all of the following conclusions assume that, do you remember that commentary from US EPA, that there's been good design and good construction, right? Do you remember the comment from remember the one that was in here, assessment recommendations? And do you remember that identified problems are classified as design, construction, and operation? And so here, thus all of the following conclusions assume there's been appropriate design and construction. And you know, over time there were enormous construction quality control and quality assurance programs put on by US EPA and related training, right? And that the operation procedures are intended to maintain the integrity, and thus the integrity of the system performance given its components. So what about the leachate collection system? The service life of the leachate collection system, okay? Use uniform coarse gravel and use it in a drainage blanket. It's a very conservative approach, and it involves using materials that are more permeable than the minimum requirements of US EPA and the minimum requirements of the BC regulations, okay? And place a suitable filter between the waste and the coarse gravel. And we've spoken about what the intent is of that. When a collection system does clog, it will result in increased head. So this is the collection system, not the filter above it. Increased head on the primary liner, causing greater advection through the liner. It may also increase the liner temperature. And those are the effects that we want to avoid. Notwithstanding that, recent data indicate that that liner may be up to about 30 or 40 degrees. Running out of highlighter pen here, probably just as well. We're at the penultimate lecture in the course. And if you're going to recirculate, which is one way of avoiding having to treat, or you're treating in situ, shall we say, you can move those temperatures a little higher again, right? And from performance monitoring, and I think I'll make this my closing comment. The rest of these conclusions are wonderful. You almost need to read the full text of the Rankin lecture to get them, but both monitoring of leakage through different primary and secondary have demonstrated that composite liners are substantially better than single liners in terms of controlling leakage, right? And that's what takes us back to the, now what do we mean by composite? Composite is the geomembrane in combination with the clay. This is a composite liner. It's a dual liner because there's another liner up here, which is not a composite liner, but this is a composite, and then there's the dual liner. So that's what Kerry is alluding to there. So I'm going to pull that closed by moving back, bear with me, to here. And there are comments. I chose to go into the Rankin lecture, and I chose to look at the leachate collection system because I think it's a perfect example of developments in philosophy, variations in the materials of the components, and thus developments of design practice with time that Kerry Rowe also observes may continue to evolve with new knowledge. And in that regard, let me leave you with this last comment, and then I'll finish the lecture of the day. In a follow-up to his Rankin lecture, Kerry Rowe in 2020, Kerry Rowe gave the 53rd Carl Terzaghi lecture to complement, nearly 20 years later, 15 years later, arguably, his 45th Rankin lecture. And in this, he spoke about some of the other aspects of design. In fact, he spoke a little bit about the integrity of the barriers and holes and drainage through the barriers themselves. And for this one, if that really turns your crank, and it is an area that either is of interest to you currently, or you may be involved in a project currently, if you wanted to pursue this further, please just go and Google it. And ASCE has that Terzaghi lecture online, and you could listen to the lecture itself. It runs for about an hour to an hour and a half or so, if you include the question period at the end. So I'm going to stop sharing it at this point, and say that concludes what I would like to say on barrier systems. It hasn't, my intent has not been to converge and give you rule after rule and suggested value after suggested value for you to turn to it as a definitive resource, but I've rather, the objective of the lecture has been to influence the way you think, such that if you need to acquire information, in order to take and defend decisions, that you can grow and nurture the ability to constructively read what you're looking at, place it in the context of evolving design practice, and take informed decisions that anybody else at this time and at this place would also do. And thus your decisions are very good decisions. Like many other things, I'd encourage you to consider the merits of field trials in advance of any significant construction works, if an owner will buy into that. And that was something I was advocating for this project on the Sunshine Coast as well. Yeah, I think that's about it. I'd say that what I see at the interface between consultants and owners at the moment is that everyone's trying to use existing waste streams and rework them into design and construction. And there, I would argue there is a role for geosynthetics in there, and insights to them are coming from works such as Kettleman Hills, such as Stark's work, and such as Kerry Rowe's body of work, amongst others. Thank you kindly. I'm going to stop the recording at this point, but I'm delighted to hang around and answer additional questions, etc. moment is that everyone's trying to use existing waste streams and rework them into design and construction. And there, I would argue there is a role for geosynthetics in there, and insights to them are coming from works such as Kettleman Hills, such as Stark's work, and such as Kerry Rowe's body of work, amongst others. Thank you kindly. I'm going to stop the recording at this point, but I'm delighted to hang around and answer additional questions, etc.